Welcome back. Today in this video we are going to see how to generate code from a B project. The code generation is focused only on the C language. Source code generation is the main byproduct of a B project. A B model represents a software executing sequentially. If several operations may execute in parallel, there is no more guarantee about the correctness of the software. No interruptions modifying the state variables are allowed. The model and the code are very close. This is called one-to-one translation. As a consequence, the code generated from it is also expected to run sequentially. The code, the body, is generated from the implementation. The generation is performed clause by clause. In this example, we can see that all identifiers are prefixed with the name of the machine, M0. Int is transformed into int32t type, and bool is transformed in bool. The abstract machine is used to generate header. In this example, the header provides the signature of the operation update x6 and the initialization. Prior to code generation, an implementation has to be proved because it's useless to generate the code of a model that is possibly incorrect, and it has to be implementable. It should comply with a subset of the B language called B0, where types have to be concrete and substitution have to be deterministic. So concerning B0 types, the implementable Scala types are int or intervals of int, bool, and defined sets or enumerated sets, or intervals of defined sets. Concrete variables, inputs and outputs operation parameters, and local variables have to use implementable Scala type as well. So it can be Scala types, arrays, Cartesian product of arrays, and functions of functions. Concrete constants, in addition to types defined above, are a subset of int or of defined sets. Concrete constants and defined sets have to be valued in the clause values, using Scala, arrays, or subset of int or of defined sets. B0 substitutions are either the sequencing of two substitutions S1 and S2, the declaration of local variables usable in X, the valuation of scalar or function, the skip substitution, if then else, case, while loop, and operation call, being operation from an imported machine scene, or local operation of the implementation. B0 expressions and predicates enable to write conditions, equalities, inequalities. It's impossible to use f of x, addition, division, multiplication, subtraction in a condition. We must use a local variable and calculate prior to test. Implementable expressions are identifier or literal constants, access to an element of an array, addition, subtraction, negation, multiplication, and division, Boolean conditions, and array initialization. In an implementation, specific lemmas are generated to ensure that the B0 code is well defined. For example, for addition, subtraction, multiplication, the result should be of the same type. For the division, the denominator should be different from 0. And for f the x, f should be a function and x belongs to the domain of f. Basic machines are specific B components. Their role is either to provide an interface with software not developed with B by calling third-party libraries or using low-level input-output services, or to provide values for types and constants outside the generic B model. The abstract machine defines the variables implemented and the operations made available. There is no refinement. The implementation is provided as source code by the developer. There is no formal guarantee that the source code of a basic machine is correct. It should be tested against its formal specification by using traditional testing means. To avoid errors in basic machines, follow these two advices. First, write a trivial implementation with skip substitution, for example, then generate the skeleton of the implementation with the code generator, and finally complete the skeleton manually. and only declare concrete data in the basic machine in order to ease code association. In this example, we are going to create a basic machine, generate code, and complete the skeleton. We have a stateless machine called measure, which provides two services, measure level and measure conception, which return several values. In the real world, these values come from sensors. The specification only requires to get 2 or 3 values in given intervals. These values are defined in a complex machine. Now let's generate the implementation for this component. And replace the specification of the operation by skipped substitution. Now we generate the code. And we get access to the source code generated. 2 files have been generated, the header file and the body file. The C file is used as a skeleton. The content of the 2 operations has to be completed manually to get, for example, the values from external sensors. We can, for example, set the value of both variables to 0. So there is no verification at this level, and if I enter a negative value, the whole program will go wrong. For example, if I make a mistake here. So some testing is required on the manual code to check that measure level and measure conceptions post conditions are met. Generic code generator gives generic code. To adapt to diverse coding rules, several translation profiles are available: C90, Light, and 01. There is also a profile called Project, where you can define your own preferences. Do not mix translation profiles among your components, or you are likely to get compilation errors. In this example, we are going to see how to fine-tune the code generation. Let's start with the M0Y implementation that contains 3 variables, 2 integers, and 1 boolean. When we generate the code with the default profile, we obtain, as expected, a header file, which includes stdint and stdbool, and a C file which contains the variable's declaration and the initialization. Int is translated in int 32-bit, and bool is translated as boolean. UID16 type, that is an integer defined in a C4b type machine, is translated as UID16 type. The C4b type machine is included in the Atelier B installation directory in the subdirectory press include. These concrete constants allow to precisely define the type used by the code generator. Code generation may be performed at either component level. In this case, the components are selected one by one and then translated using the translation profile defined, or either at project level, all the implementations are translated. The component selected is a top-level component, and initialization of all components is performed at this level. Optionally, a makefile may be generated to automate the compilation. In this example, we are going to see how to generate code at component level and at project level. In our project, we have 4 components linked at this. So we can select each implementation and generate code one by one. and we get the two header files and the two body files. So we can separate them. Obviously, top-M component is a top-level component in our project. So we can initiate the translation of all the components linked by the imported by top-M. And we can select the generation of the main component as well. So we can see that the four components have been generated, including a make file that will automate the compilation, and the main components that call the initialization and the service appearing on the top-level component. Let's consider a software which has to integrate a B software for its safety-critical part. It has an entry point and contains code related to the non-safety related part. It is connected to a B software through the operations appearing in the top-level component. Then the B software is connected to basic machines. Basic machines ensure a connection with low-level software and possibly the underlying operating system. You now know how to generate source code from a B project. This is all for today. See you soon and be formal.